Good afternoon to all of you. In last lecture, we have started our new chapter, that is baseband pulse transmission. In this one, we have to see match filter. In every communication system, ultimately we desire to fetch your original signal m of t. So for this one, your receiver output, it must give output signal to noise ratio, that is a S0 or N0. This should be larger. This is the ultimate aim of every receiver in your communication system. To get this one, we have to design such a filter which will give the maximum signal to noise ratio. Here in this match filter, original signal is given as g of t, where noise is going to add, which is a AWGN noise, white Gaussian noise, x of t, which is a filter input to your LTI filter, and here we will get y of t, which is get sampled at time instant capital T. So we will get y of capital T. Here g of t is your original signal, x of t is equal to g of t plus w of t. Here w of t is nothing but your noise, that is adaptive white Gaussian noise, which is going to add in your original signal g of t. It is an input to LTI filter with impulse response h of t and h of f. At output we will get y of t is equal to z naught of t plus n of t. Or this one we can define signal to noise ratio, that is equal to S0 divided by N0. So whatever the power which is contained by your signal g of t, which is filtered out from the filter, it should be very much larger than n of t. When this condition is satisfied, then we will get this output signal to noise ratio will be maximum. So to get this one, we have to design such a filter with an impulse response h of t, which will maximize the output signal to noise ratio. So here we can define this output signal to noise ratio, that is g0 of t square divided by expected value of n square of t. Here output signal to noise ratio, that is equal to instantaneous power or the signal g of t naught, which is a filter output, to the average energy or your noise which is get filter output, expected value of n square of t. This is the output signal to noise ratio. Now we have to find out this value and this value. So in last lecture we have find out this g0 of t. It is nothing but inverse Fourier transform of integration over minus infinity to infinity. Filter response is h of f multiplied with your input signal g of f into e raised to j 2 pi f t. Or this one we have to find out its square value. Similarly, we have to find out the expected value of n square of t. So here we will get integration from minus infinity to infinity h of f into g of f e raised to j 2 pi f capital T df square divided by expected value of n square of t is capital N by 2 integration over minus infinity to infinity h of f square df. This is regarding your output signal to noise ratio. It is nothing but instantaneous power or the desired signal and mean square energy or your noise, which is given as this one. So here for this numerator we can apply the square inequality theorem. From this theorem we can say that phi1 of x and phi2 of x, these are the two complex functions. From this theorem we can say that phi1 of x and phi2 of x, these are the two complex functions in real variable x and satisfying the condition, that is integration over phi1 of x square dx and integration over minus infinity to infinity phi2 of x dx, they are less than infinity, means they are definite signal. When these conditions are satisfied, then we can see that integration over minus infinity to infinity phi1 of x into phi2 of x square dx is less than or equal to integration over minus infinity to infinity phi1 of x square dx multiplied with integration over minus infinity to infinity phi2 of x square dx. By this inequality theorem we can see that when phi1 of x and phi2 of x, these are the two complex numbers and they are having the finite energy, their multiplication, that is integration over phi1 of x multiplied with your phi2 of x square dx is less than or equal to integration over this one, their separate value. They hold these two equations are equal. This right hand side is equal to the left hand side, provided this phi1 of x, it should be equal to k multiplied with your phi2 of x complex conjugate. These two equations, left hand side and right hand side, they are equal, provided your phi1 of x is equal to k into phi2 of x. K is any arbitrary constant. Phi2 of x is nothing but a complex conjugate. Here we can see that phi1 of x and phi2 of x, in this one numerator h of f, this is the filter response. We can see that this one is your phi1 of x and similarly this one g of f into e raised to j 2 pi of t, this one is your phi2 of x. Their individual energy is finite, they are satisfying this condition. Then we can see that average energy or this multiplication is less than or equal to average energy or this combined multiplication is less than or equal to their individual energy. So by applying this condition we can see that these two terms are separate out. Here by applying this condition we can see that integration over minus infinity to infinity h of f square df multiplied with integration over minus infinity to infinity g of f square into e raised to j 2 pi f t df. When this phi 1 of x is equal to k into phi 2 of x star, that is their complex conjugate. When this condition is satisfied, then we can see that these two quantities are get cancelled. So finally we will get is less than or equal to 2 by n integration over minus infinity to infinity mod of g of f square df. Here we can see that output signal to noise ratio is less than or equal to 2 by n. Here capital N is nothing but noise power spectral density integration over minus infinity to infinity g of f square df. So here output signal to noise ratio is mainly related with power spectral density of noise capital N and spectrum of your input signal g of f square, the energy which is associated with your input signal g of f. Now here we have to find out this output signal to noise ratio is less than or equal to, and we are interested with maximum output signal to noise ratio. So here we will get maximum for maximum signal to noise ratio, and max that is equal to 2 by n integration or minus infinity to infinity g of f square df. So we will get maximum value of output signal to noise ratio, that is equal to 2 by n integration or minus infinity to infinity g of f square df. This is happen with the condition that is phi 1 of x is equal to k into phi 2 of x complex conjugate. And here we have assumed that this phi 1 of x, so we will get optimum filter response that is equal to k into g of f complex conjugate e raised to minus j 2 pi f capital T. This will hold these two equations, left hand side equation and right hand side equation, they are equal provided this condition phi 1 of x is equal to k into complex conjugate of phi 2 of x. Here we will get a maximum output signal to noise ratio provided these conditions should be satisfied. Phi 1 of x is nothing but h of f filter response. This phi 2 of x is nothing but g of f into e raised to minus j 2 pi f t. So here we can see that h of f, it should be equal to k multiplied with g of f, it's a complex conjugate, into e raised to minus j 2 pi f t. When your filter gives this response, then we will get maximum output signal to noise ratio. Are you get it? When your filter, whatever the filter, we have to design a filter with a response h of f. Input to this one is your g of t original signal, and output we will get z naught of t. So what should be the filter response? H of f, it should be k is any arbitrary constant get multiplied with complex conjugate here g of f, complex conjugate of your input signal g of f multiplied with e raised to minus j 2 pi ft. Then and then only we will get maximum output signal to noise ratio. And see here, this is a function of input signal, only input signal. Whatever the function g of f, filter response is related with your input signal. So here we have to find out its a impulse response. Write down for impulse response. Impulse response of optimum filter that is h of t optimum is k into integration from minus infinity to infinity by taking a inverse Fourier transform g of f, its complex conjugate e raised to minus j 2 pi f into t minus t tf. For real signal g of f is equal to minus g of f, so that is equal to k into integration from minus infinity to infinity g of minus f e raised to minus j 2 pi f capital T minus t df. So finally we will get k into integration from minus infinity to infinity g of f e raised to j 2 pi f capital T minus t dt. So here impulse response of filter, that is equal to k into g of capital T minus t. So we can say that here impulse response of a filter which will give the maximum output signal to noise ratio, it is a function of input signal. This input signal is a shifted version, or we can say that it is a delayed version and scale version. It is get multiplied with your k, that is your any arbitrary constant, g of capital T minus small t, that is nothing but shifted version. So here we can see that suppose this is the input to your filter, this one is your filter, input to your filter is g of t. At output we will get, it's a delayed version g of capital T minus small t, and it is scaled by constant arbitrary constant small k. So in this way this filter is known as match filter. Because it is match, the role of this filter is to match the output, that is g naught of t, to the input g of t. It is just delayed and scale function of your input. That's why it is called as match filter. Write down this point. Here impulse response h of t optimum is a time reverse. H of t optimum is a time reverse and delayed version of the input signal g of t, except for the scaling factor small k, except for scaling factor small k. Therefore it is known as match filter. Therefore, it is known as match filter. Right to next point. Property of match filter. The peak pulse signal to noise ratio. The peak pulse signal to noise ratio of match filter depends only on the ratio of peak pulse signal to noise ratio of a match filter depends only on the ratio of the signal energy to the power spectral density of white noise at the filter input. This property says that the peak pulse signal to noise ratio is a function of signal power, the power which is related to your signal, and power spectral density of your noise. In last lecture we have used this property, that is output signal to noise ratio is equal to EP divided by capital N. This is the property of match filter. We have to derive this property. Write down the Fourier transform of resulting match filter is given as G0 of f, its Fourier transform, that is equal to H of f, which is a optimum filter response. H of f, it will give the optimum response. To get a output signal to noise ratio, it's a maximum value, get multiplied with frequency response of input signal G of f. Here this filter response for optimum case, it is given as K multiplied with complex conjugate of input signal G of f into G of f e raised to minus j 2 pi f capital T. Here this optimum filter response is given as K multiplied with its a complex conjugate G of f into e raised to minus j 2 pi f t. So this is written as K into mod of G of f square into e raised to minus 2 pi f capital T. In this way we can find out this G of f, output of this one. So we will get this Z0 of t, that is equal to integration from minus infinity to infinity G of f e raised to j 2 pi f capital T df, that is equal to K integration over minus infinity to infinity G of square into df. We can find out the G0 of t by using inverse Fourier transform, which is given as K into integration from minus infinity to infinity G of f square df. Here G of f is nothing but input frequency response. So according to Rayleigh energy theorem, write down, according to Rayleigh's energy theorem, the integral of square magnitude spectrum of pulse signal with respect to frequency, the integral of square magnitude spectrum of pulse signal with respect to frequency is equal to the signal energy capital E is equal to the signal energy capital E. So here we can say that this capital E is nothing but minus infinity to plus infinity g0 of t square dt, that is equal to integration for minus infinity to infinity g of f square df. As per this theorem, we can say that integration or minus infinity to infinity square value g naught of t square in terms of frequency, it's a magnitude spectrum g of f mod square df, integration from minus infinity to infinity, is nothing but energy in your signal. So by using this principle, we can say that this this one is nothing but k into E. By using this one, we can say that input signal, this output one, that is one capital E into K. Output of your filter G of t is nothing but arbitrary constant K, which is get multiplied with energy which is associated with your input signal G of t. Here we can say that for this filter, input is your G of t, at output we will get G of t naught. So here we can say that output signal, it can be represented by is equal to K, K is any arbitrary constant, multiplied with energy which is associated with your input signal G of t. So as per this theorem, we can say that energy associated with your input signal is nothing but it's a square value, magnitude spectrum square, or integration from minus infinity to infinity. In this way we have calculated this G naught of t, that is equal to K into E. Similarly, we have to calculate the energy associated with your noise spectrum. So for this one, write down, we are having expected value of n square of t, average energy associated with your noise which is get filtered out. Here input we are having W of t, white Gaussian noise, at output we are having n of t. So expected value of n square of t, that is equal to capital n0 by 2 integration over minus infinity to infinity mod of h of f square df. Here this filter response optimum value h of f optimum, that is given as k multiplied with g of f complex conjugate into e raised to minus j 2 pi ft capital T. Is it correct? Here optimum value of this filter, this optimum value gives the maximum signal to noise ratio, that is equal to k into g of f input signal frequency response, it's a complex conjugate multiplied with e raised to minus j 2 pi f capital T. We are sampling this signal y of t for a duration of capital T. So here we will get k into g of f e raised to minus j 2 pi f capital T. So when putting this one, we will get k square n0 by 2 integration over minus infinity to infinity g of f square df. Is it clear? Magnitude spectrum of input signal, this g of t, it will give the frequency spectrum g of f, or this one, it's a magnitude integration over minus infinity to infinity magnitude of g of f square df is nothing but energy associated with your input signal g of t. So can we say that this is a capital E? So this is given as k square n0 by 2 into E. In this way we have find out expected value of n square of t. Now we have to find out your filter response or output signal to noise ratio. For output signal to noise ratio, eta max, that is given as k into E square g of t naught square divided by this k square into n0 E by 2. So that is equal to 2E divided by n0. So here we will get maximum output signal to noise ratio, that is equal to 2E divided by n0. In this way, output signal to noise ratio, we will get maximum output signal to noise ratio, that is equal to 2E divided by n0. Here E is nothing but energy associated with your input signal g of t. This energy is given as integration over minus infinity to infinity square of magnitude spectrum of g of f. This is your energy associated with your input signal g of t divided by capital N0 is nothing but power spectral density of input noise W of t. Is it clear to all of you? We have used this property in your PCM to get a maximum output signal to noise ratio. So why we are using this match filter in your communication system? In your communication system, ultimately we require output signal to noise ratio, it must be maximum. Here we are having analog and digital communication system. In analog communication system, we are having amplitude modulation system. In amplitude modulation system, bandwidth is the problem. We will get output signal to noise ratio in terms of input signal to noise ratio. We will get a line with some slope. When we are using the synchronous detector, yes, we are having the linear relation. When we are using the envelope detector, here up to the threshold point, they are having the linear equation. After that one, they are non-linear. So here in AM, bandwidth is the problem. To solve this problem, we are moving towards the angle modulation system. In angle modulation system, when we are increasing the modulation index beta, as we are increasing this beta, your output signal to noise ratio also increases, but your gamma threshold point is also increases. This is the problem in your angle modulation system. So we can say that angle modulation system is better than AM, provided it should be working above the threshold point. To overcome this point, we are having digital communication system. Here we are having the PCM. We are having the point that is gamma saturation. As we are increasing the input signal to noise ratio, that means we are increasing the magnitude of your input pulse AP at a sufficient point where this point is called as gamma saturation point. After this one, again we are increasing this value, there is no effect on your output signal to noise ratio. Here output signal to noise ratio is mainly depends upon your which factor? Number of bits. For n is equal to 2, this is the ratio. After this gamma threshold, we will get a stable outcome. These values. As we are increasing the input signal to noise ratio, there is no effect. But initially we are using n is equal to 2, we will get a output signal to noise ratio. N is equal to 4, output signal to noise ratio is increases. N is equal to 6, this value is increases. N is equal to 8, as we are encoding this signal by using more number of bits, we will get maximum output signal to noise ratio. From this discussion we can see that our ultimate aim is we have to increase the output signal to noise ratio. Here we are using such a filter, match filter, in such a way that it will give the maximum output signal to noise ratio. Input to this filter, which is a LTI filter with a impulse response h of t and frequency response h of f. Input to this filter is g of t with white noise w of t. At output we will get g of t naught and its response is h of t. We have to design such a filter which will give the maximum output signal to noise ratio. Signal to noise ratio is given as energy associated with your input signal or output signal g naught of t square divided by energy, average mean square energy associated with your noise, that is the expected value of n square of t. So to get a better signal to noise ratio, energy associated with your filter signal g naught of t, it should be larger than your energy associated with your noise. So in this way we have to find out this inequality theorem, that is output signal to noise ratio is less than or equal to this value 2 by n integration or minus infinity to infinity g of f square df. So here we will get h of f filter response in frequency h of f, which will give the maximum signal to noise ratio, that is optimum. It should be equal to k into g of f. Complex conjugate of your input signal is get multiplied with e raised to minus j 2 pi f capital T. In impulse response we can see that h of t, that is equal to k, any arbitrary constant, multiplied with your g of capital T minus small t. So we can see that we have to design such a filter which will give the maximum signal to noise ratio. Its impulse response, it should be multiplied with your constant k, and it is a delayed version of your input signal g of t. From the property we can see that pulse signal to noise ratio is a function of energy associated with your signal g of t. Capital E is given as integration from minus infinity to infinity square of magnitude spectrum g of f mod square df, and capital N0 power spectral density of your white noise, which is the input to your filter. Actually we are using this match filter. Here we are made of one assumption, that is whatever the input to match filter, it is a known to us. When we are using the PCM, yes, we know what is the input to your match filter. Is it a rectangular pulses? Yes or no? For digital communication system, where we are using any delta modulator, DPCM, any one, here we know what is the input to your filter. Here main point is match filter gives the better maximum output signal to noise ratio provided for known signal. Right on this point, match filter gives maximum signal to noise ratio for known signal.